Occasionally over the course of honors chemistry, we're going to encounter kinds of problems or skills that we really need to understand at the honors level, that we do not need to understand at the Regents level. You can consider these videos as an honors-only supplement to the other videos that we see. In these cases, I'm always going to show them as the particular lesson with a letter after it. In this case, 3A. So in 3A, what we're going to learn how to do is do multi-step heating or cooling problems. Again, this is really an honors-only skill. What we want to be able to do here is to figure out the total amount of heat energy we would need to start at a particular phase of matter and go through a phase change and wind up at another phase of matter at a different temperature. For the purpose of this illustration, we're going to start as a solid, go through melting, go to a liquid, go through boiling, and then wind up at a gas at a temperature above the boiling point of the substance. This question is shown on page 7 of your Unit 3 packet. Here it is. How many joules are required to heat 100 grams of water from negative 20 degrees Celsius to 130 degrees Celsius? What I've done here is I've represented this as a heating curve. And that's my first step of advice to you anytime you have to deal with a multi-step heating or cooling problem. Always take a moment and sketch out what that curve is going to look like. It might look like this one if you're starting below the melting point and you want to wind up above the boiling point, or it might not. Maybe we only want to start below the boiling point and wind up above the boiling point, for instance. But in this case, we have to go through 5 different segments on our heating curve. One thing that you're absolutely going to need to have in order to do these problems is the specific heat of things other than liquid water. The specific heat of liquid water is, of course, given to you on reference table B of the New York State reference tables. It's 4.18 joules per gram degrees Celsius. We've talked about that already. But you need specific heats for other phases of water, and for those, they're given on your honors reference table. The specific heat of ice is 2.03 joules per gram degrees Celsius, and the specific heat of steam that we're going to use is 1.89 joules per gram degrees Celsius. These are both approximate values, so you may have different values depending upon the reference that you're going to be using. Anytime the temperature is changing, that means that we're going to have to use our calorimetry equation, or Q equals mc delta T. That is certainly true in line segment number 1, but of course in line segment number 1 our substance is ice. So we're going to actually have to use Q equals mc delta T, but we're going to have to use the specific heat for ice. In line segment number 2, our substance is melting. So for that we're going to have to use Q equals mHF. In line segment number 3, the water is completely a liquid and its temperature is increasing as we heat it. So for that we'll use Q equals mc delta T with the C value for liquid water given to us off of our regular reference tables. In line segment number 4, our substance is boiling, so for that we're going to use Q equals mHV. And then finally, in line segment number 5, the water has completely been converted to steam, and its temperature is increasing. So for that we'll use Q equals mc delta T with the specific heat of steam. What I'm going to do now is just plug in all the values that we're going to use. That's going to look like this. Take a moment, look at what I've done here, and if you have any questions about any of it, now would be a good time to pause the video and write those questions down. Do you understand why I've used particular specific heat values for particular equations? Or why I'm using HF and HV in the spots where I am using them? If you don't, you absolutely should write down those questions and make sure to get the answers that you need. Now that I've got all of my equations set up, it's just a matter of calculating out in order to get the answer for each of these line segments. Finally, what do I have to do in order to be able to figure out the total amount of energy needed in order to start at the beginning of interval 1 and end at the end of interval 5? It's probably obvious that I just need to add these things together. And so when I do that, I'm going to get a total amount of heat needed. 310,930 joules, which if we use our significant figure rules is going to become 311,000 joules. Does this make sense? If it does make sense, then you're probably in a great place. You can do any sort of heating or cooling multi-step problem that I'll require of you. A lot of times, the problems that I'll require will just have you start at one phase and wind up in the next phase up. So you won't have to do all 5 equations put together. But the all 5 equation version put together is sort of like the king gorilla of all of the multi-step heating problems. If you can do that and it makes sense, then we're doing fantastic. Thanks again for watching this video on how to do multi-step heating and cooling problems. Take a moment and make sure that you can solve them by moving through all the 3 phases of a substance, particularly with regard to water, because water tends to be our go-to substance here in chemistry. If you have any questions about anything that you've seen here, you can always leave them in the comments below the video or get in touch with me through the information in the info field. Thanks again for watching. I really appreciate it. Have a great day.